seminar to be delivered by Dr. Sanjay Shukla, and in meantime also we will get some feedback from the work what Mr. Rajendran is doing in the area of hydrology here. You may be knowing that Mr. Rajendran is a PhD scholar here working with us and has registered at University of Florida. So it's one of the few things what is happening between the ICRISAT and University of Florida collaboration, which is quite long standing. And as you know, we had earlier also student from University of Florida, and that is now Dr. Kiera. Now she is working in the Canada as a postdoc, and number of training courses have been done jointly in the area of watershed management as well as in the area of systems modeling, and some more courses are proposed in the area of wastewater management and also watershed management in due course of time. So let me take the privilege of introducing Dr. Sanjay Shukla, who is the associate professor and working at the research station of in the South Florida under University of Florida. He has done his bachelor's from the University of Allahabad, master's and PhD from Virginia Institute in US, and has specialized in the area of sustainable management of natural resources and particularly the water management. And what we will be hearing from him is the hydrologic modeling and decision support for evaluating environmental services. And that is the area basically what we are really strengthening in the system at ICRISAT as well as in the semi-arid tropics, because not much work has been done in really quantifying the environmental services and harnessing the environmental service as an enterprise for sustainable livelihoods for the people who are involved in it. So without much ado, I will request Sanjay to take over the podium and give his seminar, and we look forward to hear the new innovations in the area of water management.
Thank you, Dr. Vani. Good afternoon, everyone. I just want to, before we start, I see some familiar faces, and I presented, I think 2 years before, a seminar on water storage. How many of you were there in the last one? I see some hands. Okay. So the reason I ask, because it's kind of, we have added the ecological modeling part in environmental services from the same concept. So I just wanted to see how much of a kind of background I need to provide. And the presentation is that I'm going to present on some of the things my program is working at UF. And then at the end of that, then I will ask Rajendra, who, as Dr. Vani mentioned, he's a PhD student and at UF and working here right in India on looking into the effect of climate change. So we'll follow up with that. So the title is Hydroecological Modeling and Decision Support System for Ecosystem Services. And of course, all of you are familiar with that agriculture not only provides food and fiber, but also, especially recently, has been well recognized, especially post 2000, as an landscape which can also provide additional environmental services such as water storage or flood attenuation or carbon sequestration. So there are different services, and of course, all these services are not really linear. That you have more water storage, that doesn't necessarily mean that. So we have this project. This is the only project I know of where this project has been implemented and farmers are currently being paid to provide these services. This is the only project, at least in US, where actual quantification has occurred and it has been verified. Because there is a lack of data on actual quantification part. There's a lot of qualitative work, so that's what I want to present today. And briefly, I'll give you a background of what my group does. I have a water resources engineering program at South Florida, which is part of Ag and Biological Engineering Department. And we're looking into, as Dr. Vani mentioned, watershed scale, both water supply as well as quality issues. And then recently, in order to kind of make it more systems approach, we are also adding the ecological aspect. So we're working with biologists to add that component, especially to the modeling. But so the recent project we have worked on is we have large lysimeters where we're trying to quantify the biofuel crop water use and different crop water use and scale that up at the watershed scale to see what the impact would be. We're looking into wetland water basically dynamics as well as water quality. We're also looking into recycling some of the water from agriculture and recycling that drainage water for as an alternative source of water supply. So my group does both measurement as well as modeling in mostly South Florida, but right now we're also similar approach. We have a project in Tanzania. We're looking into rice production system. And then we're looking into a large scale here, a water harvesting approach where we can use some of the storm water, detain it, similar to what you have a check dam concept, but in a way it's different that you have to recycle that water, reuse it, and also reduce the flood impact of flood. And then, of course, the traditional irrigation management, trying to reduce the water consumption so that we have environmental flows, stream flows are not impacted. So with regard to environmental services, this project started back in 2007, where the idea is simple. In South Florida, your hydrology will be somewhat similar to Kerala. Coastal system, shallow water table. A lot of that really was a shallow water table and wetland throughout that. Historically, around 1900s, it was drained. So all of that was drained. So what happens now, and it has a very high rainfall, around 1500 centimeters. So you have 150 centimeters, I'm sorry. And then you have large rainfall, mostly they come during summer. So earlier when the rainfall used to come, especially between June and November, October, and you must have heard of hurricanes in Florida, right? So you may ask, in subtropical Florida, we have a drought in Florida in spite of that water, and most of that is driven by the fact that a lot of that landscape which used to have water has been drained. So there is the watershed storage has been lost. And there is a Everglades National Park, which is also United Nations UNESCO Environmental Heritage Site. And the idea is this is a river of grass where we're trying to, and it's kind of getting impacted both in water quality because all the drainage coming from agricultural as well as urban areas from north. And so water quality is impacted and you have very high flow coming in. So you're also changing the ecological diversity for worse. So the idea, and there are different BMPs, voluntary program, but and then state is spending a lot of money in building large reservoirs. But whenever you are building large reservoirs, it comes at a cost. So everything has a cost in terms of whatever water you are storing there. It may be 100 or $50 per 1,000 gallons. So there is a cost because now you have to build a large reservoir, you have to hire people to maintain it. So the concept of payment for environmental services comes from the fact that, okay, most of the land holdings here are in agriculture. So is it possible that we can pay the farmer who has the land And if he or she is willing to store water to provide the flood attenuation or treat water for state's benefit, then he or she should be paid for it, because there is a cost to treating water as well as storing water. So that's the concept. That's where the PES, payment for ecosystem services concept, comes from. And there is a large scale storage which is still needed in spite of constructing large reservoirs. And that's around 1.3 million acre foot of storage is needed. That's a lot of storage which we need to, and this is in order to overall restore the environmental flows in the rivers as well as in lakes, as well as restore the partially restore the Everglades ecosystem. So this is where it was a project led by actually World Wildlife Fund, and I'm part of the project where we are doing the hydrologic modeling as well now ecological modeling. And the concept was that we are going to select and first provide the proof that actually it can be done. That you can have water storage on agricultural land, it can be measured and verified, and therefore the payment can be done. So it's not a voluntary approach, that a cost share approach that you do something and it's assumed that you're doing it. It's based on payment, based on performance. You store water, you get paid. You treat water, you get paid. But the main idea was that, does it work? Basically quantifying the ecosystem services, that does that work? If a grower wants, if an agricultural landowner wants to provide that, how much of the services are provided and who's going to pay for it? So this program started with World Wildlife Fund, and then USDA, United States Department of Agriculture, Kellogg Foundation. They pulled the money together to kind of test this concept. And then I am involved. I'm the working as a PI for the hydrology part, looking into quantifying these two services. Because those are the two services: water storage and water quality treatment. Carbon we have not added yet, because there is of course complexity, but that's something future we will work on. So this is a multi-institutional project where my program is leading the effort for researchers in the quantification of actual services, and WWF of course is managing the overall program delivered to the state for its implementation. And we have different institutions involved, different universities, as well as state as well as federal agencies which are involved. So it's a very multidisciplinary: ecologists, economists, engineers, scientists, soil scientists on the project team. This was one of the project, and this is quickly I'll go over it just so you can appreciate. Imagine if you have a large pond. A lot of agricultural holdings, you may have a large pond, and here this is really large, around 5,000 acres. It was just in natural area. Someone owns it and says, okay, there is this canal, and there is a large nutrient load going into the lake, which they want to stop. So the idea is you pump that, go through this wetland system, measure inflow and outflow, and quantify how much water you have stored, because now it's not going to the lake, so it's not going to flood it. And then also the better water quality is improved. So the idea is how much of nutrient, nitrogen, and phosphorus can be treated, and how much water can be stored. So we have an extensive monitoring system, and I'm just one slide I wanted to share overall results. What we found really is that this system could treat almost 80% of the phosphorus going through that large canal into the lake. So, and with regard to the nitrogen, it was around 44%. So, and we have the mass of nitrogen and phosphorus retained in that. So we provided, this is average of 3 years of data, putting the whole water and nutrient fluxes together, combining all of that, and that's the final result. So for every pound of phosphorus, for example, right now, it's costing the state around somewhere between 200 to let's say $500 per kilogram of phosphorus treatment. And here you're talking about hundreds of thousands of phosphorus treated. So the idea is that money could be to the alcova. Then the main thing I wanted to present today is, so that was the water quality side. Then we have some water storage side. And that's what I want to present, the ecological modeling we have done. So the idea is that if you store water, earlier there are large flows, if you back up the water, you're going to store a lot more water. That may also, so far we are only focused on water quantity and quality. You have additional storage. But what happens to ecology? How about the biodiversity? How does that respond? So this is the EPA STAR project. In this existing project, we added the hydroecological model to look into different scenarios. Is not only how we can enhance or increase the water storage, but what is the optimum water storage for which we also get the optimum biodiversity. For example, amphibians or wading bird population. So in this project, we're looking into the lower food chain in terms of, and so for example here, you have water availability. By backing the water, you are going to increase water availability. So of course, you are retaining water, improving water quality. So that's the ecosystem services, those two, right? Water quantity and quality. Then our assumption is that the biodiversity will also respond as you increase the water availability, fish population. And that's an assumed relationship. Actually, it may be a response that fish population may increase and therefore the bird population will increase. Frogs, there is a optimum water level, and that's where the ecologists, they have provided these relationships. Or the hypothesis is that those biodiversity measures will respond in that, but we're going to test them. And then again, the native plants versus invasive species, as well as forage quality, meaning ag production. You don't want to store water and reduce the production. And if the production is reduced, how much will that be? And then there are stressors, meaning you're increasing the water ecosystem services, but by having additional water, you may increase some of the stressors. For example, invasive species, increase mosquito population, which is, of course, has a both positive and negative connotation, mostly negative effect with regard to cattle health. If there is a cattle, you have a disease, so there is an increased mosquito population. So there are also some stressors we are looking into, and then you have invasive species. How we don't want to have that, increase. So there is a balance. So this project looks into trade-off of water storage and treatment versus the biodiversity, and how does the trade-off. So overall approach is that we are going to look into these as you have in different wetlands in the farmland. How does that respond as you increase the water storage? How does the biodiversity change? That, and then we are using a finite difference model, mini complex coupled model, surface and groundwater, Mike Shee, Mike 11 model. It's a hydrologic and hydraulic model. So you combine that, you can predict for different level of water storage, how will the wetland water level change. Based on that, then you develop a hydroecological relationship and you predict for different level of water storage, how will the biodiversity respond. And then you integrate that within a decision support system we call multi-criteria decision analytics. And I'm going to go in that. But here, we're looking at a larger scale, a watershed scale, spatially distributed modeling, because for different wetlands, we really need to predict the water levels in the wetland. So for example, here, the biodiversity measures, we're looking at really a small scale, maybe 10 acres, 50 acres, maximum 100 acres. At the watershed scale, we are looking at as large as 20,000 hectares, 20,000 acres. And then, of course, you're looking at, so the idea is biodiversity, water retention is being measured at the watershed scale. Biodiversity, we are measuring at all these wetlands. And you integrate those two and scale it up to larger watershed and see what the effect of those, how the ecosystem services will respond. And the idea of water storage, I didn't go in detail. Really, there are ditches all around here. And earlier, there were no ditches, there were no drainage. So the idea is at the outlet, they've installed these structures and they put these boards here, so you back up the water. The idea is to increase the storage. And then as you increase the storage, this is a small movie using the actual data. So when you have a downstream water level, you increase that storage, then you have inundation increasing, from all sides, but mostly from the downstream end here, the water, as you can see, the hydro period of these wetlands will change. And that's what we are going to link this to biodiversity. So we have now inundation and storage, landscape as well as landscape, wetland scale, as well as biodiversity. So that modeling for hydrologic modeling is done in spatially distributed model, 120 meter grid, so that each wetland water level, surface and groundwater level can be quantified. And I'm not going to go in detail, but we have a very detailed monitoring network using eddy flux to quantify evapotranspiration, flows, as well as the groundwater levels at the outlet. And as you know, for example, at this watershed, there are all these structures you see, they all look like that. And the idea is here, you don't let the water come in downstream until a certain stage is reached. So you're kind of mimicking the natural system the way it was before. So today I'm just going to share the data for these 3 wetlands. We just finished that and we're still working on that. And in terms of with regard to hydrologic modeling, how we are using that is that for different water levels of storage, we're going to predict what the water level in the wetland would be, what the how long that wetland was wet before and will be now in the restored condition. And then once we know that hydrology has changed, then we're going to have to develop the hydrologic and hydroecological relationship. So now you know all these wetlands, how they're going to respond, and then you're basically trying to predict how the biodiversity will respond. We have calibrated and, of course, validated the model using the long-term data, and that's just the calibration validation part. I'm not going to go in detail. This is, something Florida Ranchland Environmental Services Project. That's the scenario we are running. So, for example, you can see that the baseline here, we had much higher flows. This is discharge, and once you, of course, install those structures to manage that, you are able to reduce the peak flows, and you can shave off the peak, and the hydrograph looks much more like a natural system. So for each of those scenarios at different levels, so let's say for every 6 inch, we keep on varying that, and now we have for all these wetlands different hydro periods, different inundation frequency, how long they get wet, because ecology respond to that. I mean, you need to have a minimum. All of these different invertebrates, for example, have a life cycle. And so that life cycle has to be matched with how long that system needs to be wet. So for example, for a wetland, I'm showing for that specific watershed, you have a wetland and you have a depth of water. And that's our biologist. They are collecting the data and they're providing that so we can kind of do the hydroecological modeling. So you can look into, for example, the fish population at different wetlands. How does that vary as a function of for the same wetland? As you can see, from 27 to 33 centimeter, the fish population goes from 3 to 31. It's a big jump. But then, of course, it when you go to 33 at another time, you have some variability, which is part of the natural system. So you have fish, frog, invertebrate. We're not looking into birds, but the idea is that overall food chain, if you can provide that, then you can perhaps add that mammals and birds later on. So inundation, then we have a GIS-based model, which we can look into inundation areas of different wetlands, for low and high. And under different low and high, we have taken the measurement. So we know the inundation area, frequency, and network connectivity. Like, the different, some of the deeper areas are connected to the shallower area. And using that, then we are trying to link, and this is where we are still working on, hydrology to biodiversity. For example, you have the system goes from really small inundation to large. How does the biodiversity respond? looking into frequency of inundation, meaning how frequently is it getting wet compared to what it was before. Area wetted, larger area versus small area, percent of the area, and the volume. Stage, time since filling, especially the mosquito, for example. You have really dry area and then you have a rainfall and mosquito population jumps. So that for different biodiversity measures, different hydrologic metrics are important. So we were exploring a lot of that flashiness, how fast does the system change, and how does does the ecology respond to that. So these are the preliminary relationships we find, for example, invertebrates and wetland plants. We have very good relationships. Frogs, you go there sometime and you find a frog, and sometime you go there, when there is water, there is no frog. Highly variable. So you need a larger data set to really develop a model which we are collecting more data. Fish, we have a somewhat of a relationship. So this is the hydroecological relationship, for example, for fish abundance. So really, I was surprised, and my biologist colleague were surprised. Usually, you don't see that kind of good relationship between inundation area and time since filling. That's a model. It's a multivariate model. I was able to develop. So it's a multivariate statistical model using stage, inundation area, and time since filling. It's a step by step. You go through all the variables, and that's the best model. And it was significant, and the R square is around 0.2. That means that using the stage and hydrologic variable, we are able to predict fish population. And higher the fish population, of course, means more, bird population is going to respond accordingly. Now, will that be linear or not? We don't know that yet. But we are right now focused on fish population. Richness, if you don't know that refers to different kind of species. So how many kind of species are there? We want the diversity as well as the richness in terms of we want different kinds of fish. That we really couldn't predict very well. Overall fish population was good, but the model is not good, or right now hydrologic parameters are not able, we are not able to relate to richness. Frogs, abundance, we couldn't find anything. In terms of abundance refers to the number of frogs. Richness, we were able to find some relationship, but really it was not statistically significant. Invertebrate, really these are the insects and flies and beetles. And that relationship we were able to, this was the best relationship. We were really able to quantify as percent inundation, time since filling, and inundation area. We are able to predict what the invertebrate number, how the number will respond. And even the richness in this case, we are able to predict, which is statistically significant. Crayfish is a special, of course, insect in terms of its important. Abundance-wise, of course, there is no richness factor because there is only one type. Abundance, the relationship is really not that good, meaning statistically not significant. But again, this is only 2 years of data. We're going to add some more in different wetlands, see if we can improve on that relationship. Plant, as you know, ecological, diversity is very much driven by the plant. When I say plant, meaning obligate plant, these plants are the plants which thrive in wetland environment, and they are natural, they are not invasive plants. So that we were able to predict very well. But what we also find here is that if that's how it is, that as you increase the inundation area, you're going to have some of the forage losses. Your productivity is going to be lost because now there is wetland species are coming up, and this is where the trade-off comes in. Because you're storing water, you're providing that service, your diversity is better, but now that comes at a cost of reduced productivity. So this is where the trade-off comes in, and that's where the optimization comes. So in future, we are going to, and I have a graduate student, 2 of them, and a postdoc who's working on basically doing the Mike-Shee modeling for different scenarios at all the 8 sites, and developing these hydroecological relationship and integrate that within a multi-criteria decision analytic system. All that means is that if you are a farmer, and if you are a state agency, and if you are a World Wildlife Fund or NGO, all three of you may have a different desired outcome. As a state agency, you want to see the most important thing because the legislator or the politicians, they want to see the Everglades restored. They want to see the water supply being maintained. So water is the most important thing. So for you, the water is most important thing. But someone else, for example, the Fish and Wildlife Commission, may be saying, well, water is important, but hold on a moment. We have some of the species, endangered species. We don't want to adversely impact that. So the idea is that for the same service, even the water storage, different clientele group or different stakeholders will have different rates. And this is where the MCDA comes in, where we are able to kind of simulate, ask them for their preference and simulate, like you're sitting in a room with environmentalists and state agency, all of you can discuss and say, okay, this is how important it is for me to store the water. Farmer may say, well, for me, most important thing is I don't want to lose forage and I want to get paid. And I want to get paid enough to offset that. So that's where we are kind of, it's called a decision support system we are developing where we are able to kind of look into different alternatives, that's impact, opinion in terms of how much do you value. That's where you assign the weights. So you can look into as you vary in a group, as you vary the weights, how does the overall outcome get impact? And based on the overall ranking, then you can decide, okay, which alternative provides enough water storage and at least does not do any damage to ecological diversity and does not reduce the income drastically and also pays for the environmental services. So that's the environmental service software we are developing right now. For example, for different alternative cost of, say, for example, cost and uncertainty, different parameters you can add to look at the overall ranking. Alternative one got a ranking of let's say 7, and alternative 2 got 3, and so you have different alternative, you have different ranking system, and among that, then you can select top 2 or 3, and then you can vary depending on where you are providing these services. You can select. So with that, I will want to acknowledge EPA STAR, which funded this project. And with that, I'll end and ask if you have any question. Otherwise, I'd like Rajan to present some of the work he's doing.